Okay, this will be the last section that we cover, section 12.5, entropy. Let's start the PowerPoint. All right. State variables in thermodynamics can be used to describe the thermodynamic state of a system. Temperature, which is associated with the zeroth law, and internal energy associated with the first law are both state variables. A state variable called the entropy S is related to the second law of thermodynamics. On a macroscopic scale, we define entropy just like the German physicist Rudolf Clausius first did in 1865. Let Q be the energy absorbed or expelled during a reversible constant temperature process between two equilibrium states. Then the change in entropy during any constant temperature process connecting the two equilibrium states is defined as in the equation shown. If we want to calculate delta S, the change in entropy during a transition between two equilibrium states, we need to find a reversible path that connects the states. We take this calculated entropy change to be delta S for the actual path. We need the approach because quantities such as the temperature of a system can be defined only for systems in equilibrium, and a reversible path consists of a sequence of equilibrium states. The subscript R on the term QR emphasizes that the path chosen for the calculation must be reversible. The change in entropy, delta S, like changes in internal energy, delta U, and changes in potential energy, depends only on the endpoints and not on the path connecting them. Entropy is an important concept because the entropy of the universe increases in all natural processes. This is another way of stating the second law of thermodynamics. Although the entropy of the universe increases in all natural processes, the entropy of a system can decrease. For example, if system A transfers energy Q to system B by heat, the entropy of system A decreases. This transfer can only occur if the temperature of system B is less than the temperature of system A. Because temperature appears in the denominator in the definition of entropy, system B's increase in entropy will be greater than system A's decrease. So taken together, the entropy of the universe increases. For centuries, different people have tried to build perpetual motion machines that operate continuously without any input of energy or increase in entropy. The laws of thermodynamics make these machines impossible. In all natural processes, there's a large element of chance. The spacing between trees in a natural forest, for example, is random. If you discovered a forest where all the trees were equally spaced, you would conclude that it had been planted. In the same way, leaves fall to the ground with random arrangements. It would be highly unlikely to find the leaves had fallen in perfectly straight rows. From these observations, we can say that a disorderly arrangement is much more probable than any orderly one if the laws of nature are allowed to act without interference. Take the two card hands shown in the photos. Imagine if you were playing poker. The left photo is a royal flush, a highly ordered hand with a low probability of occurrence. The right photo is of a disordered and worthless poker hand. The probability of this particular hand occurring is the same as that of the royal flush. There are so many worthless hands in poker, though, that the probability of being dealt a worthless hand is much higher than that of being dealt a royal flush. Entropy is an important concept in thermodynamics, but it is also very important in the field of statistical mechanics. In statistical mechanics, the behavior of a substance is described by the statistical behavior of the atoms and molecules contained in it. One of the main conclusions of the statistical mechanical approach is that isolated systems tend toward greater disorder, and entropy is a measure of that disorder. Here's another way to calculate entropy. Where K sub B is Boltzmann's constant, and W is a number proportional to the probability that the system has a particular configuration. The symbol ln again stands for natural logarithm. Imagine that you have 100 marbles, 50 red and 50 green, in a bag. You draw one marble, record its color, return it to the bag, and draw again. Now let's say you continue this process until 4 marbles have been drawn. Note that because each marble is returned to the bag before the next one is drawn, the probability of drawing a red marble is always the same as the probability of drawing a green one. The results of all possible drawing sequences are shown in the table. For example, the result red, red, green, red means that a red marble was drawn first, a red one second, a green one third, and a red one fourth. The table indicates that there is only one possible way to draw 4 red marbles. There are 4 possible sequences that produce 1 green and 3 red marbles, 6 sequences that produce 2 green and 2 red, 4 sequences that produce 3 green and 1 red, and 1 sequence that produces all green. From our equation, we see that the state with the greatest disorder, 2 red and 2 green marbles, has the highest entropy because it is most probable. On the other hand, the most ordered states, all red marbles and all green marbles, are least likely to occur and are states of lowest entropy. The outcome of the draw can range between these highly ordered, that is lowest entropy, and highly disordered, highest entropy states. We can think of entropy as an index of how far a system has progressed from an ordered to a disordered state. The second law of thermodynamics is really a statement of what is most probable rather than what must be. Imagine placing a block of ice on a brick patio as shown in the figure. There is nothing in nature that absolutely forbids the transfer of energy by heat from the ice to the much warmer surface. Statistically, it is possible for a slow-moving molecule in the ice to collide with a faster-moving molecule in a brick so that the slow one transfers some of its energy to the faster one. When we consider the great number of molecules present in the ice and bricks, the odds are overwhelmingly in favor of the transfer of energy from the fast-moving molecules to the slower-moving molecules. As this example shows, a system naturally tends to move from a state of order to a state of disorder. The initial state, in which all the ice molecules have low kinetic energy and the tabletop molecules have higher kinetic energy, is much more ordered than the final state after energy transfer has taken place and the ice has melted. The second law of thermodynamics defines the direction of time for all events as the direction in which the entropy of the universe increases. Even though conservation of energy isn't violated if energy flows spontaneously from a cold object, the ice cube, to a warmer object, the tabletop, that event violates the second law because it represents a spontaneous increase in order. Imagine making a film of the melting ice cube, speeding it up and running it backwards. It would look very strange to see the water form into ice. This tendency of nature to move toward a state of disorder affects the ability of a system to do work. Think of throwing a ball against a wall. The ball has kinetic energy and its state is ordered, which means that all the atoms in the molecule of the ball move in unison at the same speed and in the same direction, apart from their random internal motions. And apart from that, their random internal motions, that is. When the ball hits the wall, part of the ball's kinetic energy is transformed into the random, disordered internal motion of the molecules in the ball and the wall, and the temperatures of the ball and the wall both increase slightly. Before the collision, the ball was capable of doing work. You could drive a nail into the wall, for example. After some energy is transformed into disordered internal energy, this capability for doing work is reduced. The ball rebounds with less kinetic energy than it originally had because the collision is inelastic. We can talk about grades of energy. Let's say we have 2 kinds of energy, A and B. If A can be completely converted to B, and vice versa, we say that A and B are of the same grade. On the other hand, if A can be completely converted to B and the reverse is never complete, then A is of a higher grade of energy than B. In the case of a ball hitting a wall, the kinetic energy of the ball is of a higher grade than the internal energy contained in the ball and the wall after the collision. When high-grade energy is converted into internal energy, it can never be fully recovered as high-grade energy. We call this the degradation of energy. The energy is said to be degraded because it takes on a form that is less useful for doing work. In other words, in all real processes, the energy available for doing work decreases. Be aware that the statement that entropy must increase in all natural processes is true only for isolated systems. There are, of course, instances where the entropy of some systems decreases, but with a corresponding net increase in entropy for some other system. When all systems are taken together to form the universe, the entropy of the universe always increases. Ultimately, the entropy of the universe should reach a maximum. When it does, the universe will be in a state of uniform temperature and density. All physical, chemical, and biological processes will cease because a state of perfect disorder implies no available energy for doing work. This gloomy state of affairs is sometimes referred to as the ultimate heat death of the universe. But don't worry about it. It's not coming for a long, long time. Okay. The human metabolism section I will leave as a self-study if you're interested in that. I think we've covered most of what needs to be covered for thermodynamics. And with that, we will end this section.